Hello, calculus fans! So in the preceding section, we found some power series for a few functions, but they were all originating from the geometric series. What we want to do now is widen our class of functions of which we can find power series representations. And by the way, sometimes we'll call these power series expansions. It means the same thing. And we'd like to answer some more general questions. Which functions have power series representations? And how can we find these representations? So what we're going to do is start by assuming that our function f of x has a power series representation and that it looks like this, the usual sort of thing. And that this representation is valid as long as absolute value of x minus a is less than r. We're going to try to determine c sub n in terms of f. So it's the known function is f, what's unknown is these coefficients. Now let's plug in x equals a. And what you should see is that if you plug in x equals a, all of this is gone. So we're left with c sub 0 is equal to f of a. So here what we've done is we've solved for what c sub 0 is. So the next thing we're going to do is differentiate term by term. So if we take our power series, which looks like this, and we differentiate term by term, we should get this here. So you should just look and make sure that when you differentiate each term, that you get some new term, and make sure you see how we got there. Now we're going to plug in x equals a again. Notice that when we do that, pretty much everything disappears. And now we're going to get c1 is equal to f prime of a. Right? On the left-hand side, we have f prime of x. Okay, let's keep going. We differentiate one more time. So we get f double prime equals 2c2 plus 3 times 2 times c3 x minus a, and so on. And now we're going to play the same game again, where what we're going to do is we're going to plug in x equals a, and everything that I've underlined here is going to disappear. Now we have f double prime of a equals 2c2. So again, we're solving for the c's. Remember, we know what f is. We're trying to figure out what the c's have to be. So now we have c2 is equal to f double prime of a over 2. All right, one more derivative. And one more time, we plug in x equals a, and all of the stuff out here gets disappears, and now we get f triple prime of a equals 3 times 2 times c3. So c3 equals f triple prime of a over 3 times 2, and so this is equal to f triple prime of a over 3 factorial. So what have we done at this point? We've solved for c0, c1, c2, c3. Let's do one more. One more derivative. F quadruple prime of x equals, okay, so go back and just make sure that you see what the fourth derivative is. And now, same game. Everything out here is going to disappear when we plug in x equals a. And so now we have f quadruple prime of a is equal to 4 times 3 times 2 times c4. Solve for c4, and we get f quadruple prime of a divided by 4 times 3 times 2, which is quadruple prime of a over 4 factorial. You'll notice that it's better to not multiply out 4 times 3 times 2. Yes, that's equal to 24, but it's better to write 4 factorial. And the reason is that now we can write down a general formula for what the c sub n's look like. C sub n is the nth derivative evaluated at a divided by n factorial. So if f has a power series expansion at x equals a, we now know what it looks like because we now know what the coefficients have to be. It has to be f of x is equal to the sum of the nth derivative of f at a over n factorial times x minus a to the nth power, which you could write out this way, sort of a longhand. This series has a name. It's called the Taylor series of f at a. Sometimes we'll say about a, or other times we might say centered at A. There's a special case when A is equal to 0. The Taylor series looks like this. The sum, where n goes from 0 to infinity, of the nth derivative evaluated at 0 over n factorial times x to the n. If you wanted to write out longhand, it would look like this. This particular case comes up often enough that we're going to give it a name. It's called the Maclaurin series for f. So when you see a Maclaurin series, we're just talking about the Taylor series of f centered at 0. Now keep in mind what we've proven. We've proven that if a function has a power series representation, then f equals its Taylor series. But not all functions have power series representations. The good news is almost all of them do. And pretty much any function that we run into in this class will have a power series representation. But it is something that still needs to be proven, that any particular function you deal with has a power series representation. And this is something we'll deal with at the end of the section. Okay, that's all for now.